work?
No, there's the good kids who clap, and then the not so good kids hear them.
Do we get everybody to sit crisscross applesauce too?
No paper airplanes.
Hey! Sure. Everybody can sit up front. There's plenty of room up front. I have no idea what the hell's going on. Hey, everybody in back. Let's come on up. Hey, it's Alex. Hi, Alex. Wow. So I'd like to thank everyone for coming to my SoundCloud rap album launch party. So once everyone gets seated, we'll get started with my SoundCloud rapper album launch party. See, they want the SoundCloud rapper. Yeah, yeah. Woo! Hey, we're here! After a very, very long break, we are back with the Didactic Galactic and also the Hardware Happy Hour, and those people are there. There's one of them. Round of applause for the Hardware Happy Hour people for teaming up for this one. Are we streaming? Yeah. We are streaming. Oh, wow. Okay. You marked this not for kids, right? Good. Okay, schedule. We had the yummy food introduction. Our speaker tonight will be Amy Qian. She will be talking about Flexures, which is bendy stuff. That's neat. And I guess we will have community announcements, and then we're going to be doing the Hardware Happy Hour thing. So somebody here said they were bringing core memory. Who's that? Yo, that's going to be cool. And then the after party at the Alchemist Bar down on 3rd Street. Okay. So let's see. Code of conduct. We have one. And we'd like to thank our fabulous sponsors, Supplyframe, Hackaday, Tindy, Fine Chips Pro. Yes. Next slide. Tindy. Hey, if people here make stuff, you should sell it on Tindy. There you go. Okay. And let's see. After party at the Alchemist Bar. So for now, I would like to welcome our next speaker. And she did this in Keynote, so I can actually probably figure it out this time. Yay. Okay, so up for our talk is Amy Qian. She'll be talking about Flexures.
Can everyone hear me? What about now? Your section was a lot shorter than I thought it'd be. Cool. Welcome everyone to this Flexure lecture. I see some familiar faces. Maybe this will be a little bit rerunny from November, but there are some new bits, so hang in there. I'll give a brief introduction about myself. My background is in mechanical engineering, and that's what I've always done professionally. But like many of you here, I have a healthy array of personal projects, and that's really where I found my biggest opportunity to explore new things and try out new things. And it's really in my personal projects that I've been able to explore Flexures a lot today. So while there are people in the world who study compliant mechanisms very rigorously or academically, I'm not one of those people. I will reference some of their work today, but I'm trying to come at this from a more kind of practical perspective, so hopefully that's something that you all will still find interesting. So just brief rundown of what we're going to go through today. Take a look at some examples of Flexures around us, talk through some design trade-offs, some factors regarding their manufacturing, and then talk about even more examples. But first of all, what is a Flexure? So Wikipedia says Flexure is a flexible element engineered to be compliant in specific degrees of freedom. So what does that mean? We have something that's compliant, so something that's bendy, and it's a mechanism. We want to use it over and over again. So really, the thing we should be talking about is springs. So what is a spring? Perhaps this graph is familiar to many of you. This is a stress-strain curve. So we have stress that's measured in force over area and strain measured in percentage elongation. So charts, people get charts like this by taking a dog bone sample of material like this and pulling it very slowly while measuring both the force and the elongation. And this makes sense, right? As let's see if I can do this. As you apply more force, you get more deformation, and you keep applying force until at some point the materials break. This particular curve, I think, is a cartoon of carbon steel. But really on this curve, the interesting part of it is this elastic region we call, which is where you can apply a force, and when you remove that force, the shape will then recover. And so that is what we like about springs. In this linear section, the slope of this we refer to as the stiffness, and that makes sense. If you have something that, let's say, for the same amount of force, ends up bending less. So you get a line here. You have a much steeper line, a much stiffer material. So staying with this curve, because I always think it's nice to kind of take these charts and build them into our intuition. So looking at this first graph over here, this is an example comparing brittle material and ductile material. So brittle, like a glass or a ceramic. You push on it, it feels very stiff, it doesn't deform very much, and suddenly it breaks. Or maybe something ductile, like mild steel or copper, where you push on it, it does have some resistance, but then it starts to bend, it's still resisting the force, and you really have to bend it quite a bit until it breaks. This over here, another comparison of just various materials, and I think it's cool to think about what is it about various materials that give them specific stress strain curves. So glasses and ceramics, for example, are often composed of things that are covalently or ionically bonded together. So these are really stiff bonds. So you end up with material that's really stiff. But the structures of those materials are such that once you've introduced a crack or something like that, it can propagate throughout the material, and so you get a fracture. Metals, on the other hand, have metallic bonds, and they have shear planes, which I like to. The image I have in my brain is of these magnetic magnetic balls as these toys. You can try and shear this cube apart, and it will resist, and if you don't shear it too much, it'll spring back into place. And so that's kind of what's giving you the spring property. But if you did shear it over, it would still be kind of connected along that plane. And so that's similar to what's happening within a metal. With rubbers and plastics, these are composed of long polymer chains, and while the chains themselves are covalently bonded, the interactions between the chains are fairly weak intermolecular forces. So I like to imagine like wet spaghetti, and as you kind of pull it apart, there is a little bit of resistance, and as you keep the force applied, they'll sort of they'll finally move apart, and then the deformation is pretty permanent. And maybe some of you have heard of plastics creeping. So when you apply a force on a plastic structure for a long time, sometimes that structure then will retain its shape, and that's really what's happening in polymers. This final graph on this slide is of Delrin, which is a material that I'll talk about a lot in the examples, because I think Delrin is really great to prototype with, especially using a laser cutter. And there's really two main takeaways from this that I want to point out. The first is these family of curves, they go from low temperature up here to high temperature up here. So really the material properties of this plastic, and really a lot of plastics, is very temperature dependent. And then the other thing to highlight is that there's really not a great elastic region here. So really, like, plastic is not a great spring. So I think that's something to keep in mind as we design things. So we'll come back to that. I promise, this is the one last boring slide. So for springs, I think many of us are familiar with this equation where the force is proportional by some constant to the amount that we deflect it. And similar, if we're imagining like a diving board, a beam, that constant is expressed by this expression here. And the main takeaway from this is, you know, if you imagine like a diving board beam and you increase the thickness of it, you now have to press much harder in order to get that beam to deflect the same amount. And if you make that beam much longer, you have to push much less in order to deflect that beam the same amount. So it's always great when the equations line up with our intuitions. So, okay, so diving into some examples. Here are some examples of flexures all around us. And I think it's cool to think about with flexures, like, when is it that you need the flexure to have constantly a spring force, or potentially only momentarily provide a spring force, or maybe a spring force is not important at all. So for example, with these are showing like leaf springs on a truck suspension. You know, those springs are always holding up a truck. You want there to always be a spring force available. So that's key when you choose like what material and how much deflection to have into a system like that. For a plastic buckle like this, during the like clipping together process, you know, the arms are momentarily deformed and then you want them to spring out. But for the rest of its lifetime, you're not. There's really like no force on those springboard members, and so given what we know about plastics and creeping, this is like a good insight to why these things being made out of plastic actually means they have like a long usable lifespan. And then things like maybe Tupperware lids or this like ketchup bottle. I think books are another good example. You don't need books to like spring open or spring close. You really just need them to be able to cycle many times. So anyway, I think that's those are all like fun things to think about as you decide what kind of flexure you want to design. These examples may be a little bit less around us, but still around us. Things like spring clips. Or these are flexible shaft couplers to take up any like axial misalignment. This is a precision locating stage. So this structure in here has been kind of cut away to allow for certain types of deformation, and then these adjustment screws can let you do like really precise motion adjustments. This is an example I really love. We'll come back to this a little more later, but this was designed as a 2-axis positioner for a thruster used on a satellite. So it's all one 3D printed titanium flexure. This one, hopefully like less all around us, but anyway, just another example of a flexure. This is perhaps an example of a flexure that is most around us. So MEMS being a kind of etching, two-dimensional like etching process lends itself really well to a lot of flexure structures. So what you have here is there's a mass that's being suspended by a set of deforming beams, and as the capacitance, there are multiple ways of doing this, but like, you know, you can measure as the capacitance changes between certain parts of the structure, and that's how you can measure acceleration. So down here is sort of like the real world version of what this cartoon would look like if it were actually working. And then I believe this here is a scanning image of a chip that's really similar to the gyroscope that's shipped with the iPhone 4. Okay, so next we'll go into design trade-offs. First I'll plug this research group. No affiliation. They just have an awesome website. You can. I've stolen a lot of GIFs from their website for this presentation. I encourage everyone to check it out. They have a lot of STL files of like 3D printed flexures that you can like download and play with. I also just wanted to highlight that the purpose of this talk is not to convince everyone to only build flexures. I think that definitely not everything should be a flexure. I just think they're a super useful tool, and so I think it's nice for everyone to have that kind of in their toolbox. Okay, so first off, flexures I think lend themselves to making assemblies a lot simpler. So here we have an example of a vice grip, and if we look at this, it has at minimum 1, 2, 3, 4 parts, not including all the pivot joints and the springs. Over here, we have an example of something that has the same movement, but is essentially just one piece. So you can imagine, because this is so much, this is one piece, you can imagine shrinking that down much more easily, depending on, the reliability of these sorts of things or alignments. Perhaps you have an opportunity to make a structure that's also much more reliable. This down here is another example. This is a door latch that's all a flexure. Now, it's been pointed out to me that you could imagine a door latch mechanism that's still a flexure that's like much simpler looking than this. But I believe this research group, they basically made a tool where you could start with like an array of like kind of like pixels where you could pick whether it was a flexure or a rigid piece, and you could kind of indicate your like desired input motion and your desired output motion, and it would kind of figure out like what all the little pixels should be in order to generate a flexure. This is that thruster mechanism that I really liked. So here you just have one central structure with 2 motors that interface with it. And now you can imagine that if that structure were to be made with traditional mechanisms, it would probably require gears or bearings. You'd have to worry about backlash, and there's a good chance that it would be bigger and heavier, which are obviously like 2 really big constraints for satellite things. So this seems like a really big win in a lot of ways. I also think when looking at this mechanism, it's interesting then to think about how much energy is being stored in the spring, kind of like the examples that I was talking about earlier, thinking about like when you want springs in these mechanisms to store energy. I don't know if they have that problem here, but definitely like the further you're trying to turn the thruster, the more torque you need to apply to the system in order to be able to do that. That's not a problem that you have if you're just turning something around a pin joint. So while I think sometimes that can be a problem, I think there are also lots of cases where that's a huge advantage. So here are some examples of that. On the top right, this is a tool changer holder designed by Joshua. Some of you might know him. He's working on a 3D printer called Jubilee. But the little white structure there is then providing a little gripping force to make the tool changes more reliable. Down here, what we're looking at is the top part of a sliding structure. So the bottom part has rigidly mounted rollers, and the top part has rollers that are mounted on this white beam, and it's very subtle, but the white beam kind of deflects as it slides across. And you really want a constant force applied to make sure that the motion is constrained. Because the beam is compliant, it can account for the fact that those 2 structures are not parallel. And finally, this is another example from Joshua. This is it's viewed horizontally. The mechanism would be used standing up. This is a pen holder. So you could imagine that perhaps the actuator for driving the pen, maybe you only need a solenoid to like push the pen down, and you could rely on the spring function of the flexure to sort of lift the pen back up. So there are downsides. I think the major one is that often, in order to be able to design like a flexure with a long life, you need to do a lot of simulation. And frankly, I do basically no simulation in any of the projects I do. There's a lot of guess and check. But like to do it right, you really have to do this. And the main reason for that is that materials fatigue. So This is an example of fatigue chart. Really, the only takeaway from this is if you deflect something just a little bit, like very far away from its yield stress, where it would have permanent deformation, you can do lots and lots of cycles of small forces before maybe that structure ends up breaking. Of course, if you push things over and over again, much closer to its yield stress, then you just won't have a very long life in that mechanism. So that's definitely a major concern with Flexure, since we're relying on the deformation of the material in order to get the motion. And of course, Flexures have really limited range of motion. So these joints work on this design, but of course, none of these are going to have like anywhere near 360 degrees of rotation. So for some mechanisms, they simply just don't make sense. Okay, but there's lots of manufacturing benefits. So first of all, I think that Flexures are just so easy for a lot of like DIY projects. Here's some examples. Because so many of them are 2D, they lend themselves really well to just sheet material. So this is an example of a wooden kick scooter I made, where the spring for the brake is just a strip of polycarbonate. Over here is a laser cut demo board, which I'll talk about. I brought some, so feel free to come click it later. But anyway, all of these structures are also just 2D and can be easily cut on a laser cutter. These shapes here also laser cuttable and 3D printed. I also think that Flexures lend themselves to being really, really robust to kind of crude manufacturing processes, if that makes sense. So, a press fit, for example, like if you're off by half a thousandth, then it either doesn't fit or it's too loose. You sort of don't have very much room to play. But with Flexures, like this is an example here where, the 3D printed plastic is probably not like spot on in terms of dimensions, but because you can design it so that it's a little bit deformable, you can have like kind of these soft press fits without a lot of like machine tuning. I think another example here is, with all three of these types of manufacturing processes, it can be tricky or require a fair bit of guess and check to make sure that all your features are like spot on the dimensions that you design them. So getting them to be really accurate is hard, but getting like the same, for example, if you design this Flexure, getting this beam here to be the same width as the other beam next to it is pretty easy to hit on with these manufacturing processes. So you can end up with like a very balanced spring mechanism using these processes. Oh, we can enjoy this bistable clicking thing. Here's another kind of design toolbox thing that I really like. I learned this from the MIT had a Machines That Make group that designed this mill, and I think a lot of these ideas and the people who worked on that ended up then working on the other mill that's made by Bantam Tools. And it features like this pin joint right here, which kind of provides like the locating feature. And on either side of it, there's these Flexure arms, which because of this interference fit, they're always like sucking the joint tightly together. So it's a really cool way to get parts like right out of the laser cutter that just snap together with a really tight fit. And I think this is probably, you guys are all familiar with this, where if you have like two linear rails, in order to prevent the over-constraint from the two axes being misaligned, you have one of them that's rigidly aligned and then one of them that's mounted in this way so that there's a little bit of compliance. Okay, this is like such an ugly slide, but anyway, more examples. This is I bought like a mesh network thing for my house, and I wanted to put this in the hallway, and of course, like it just comes with this cord and this thing, and the only way to then I either have to like mount it to the wall or like it's just like sitting on the floor. So anyway, the Flexure in this case, it's not really being used as a spring. It's really just like a nice deformable thing where the zip tie can kind of like suck everything together. This I saw walking along the road, and I think this is a pretty cool mechanism. So this is the mud guard on a semi-truck. And as it's bumping along, I would imagine that there could be quite a bit of stress in this elbow here. And so in order to avoid fatigue, I'm guessing they put in this extra loop to kind of distribute the deformation over a longer area. So pretty clever. Okay, more random projects. This is a a demo board I made just to demonstrate various different flexures. So on the top here, we have like a locking tab. I use this for a project in my car. This is just a simple ratchet wheel. Over here, this is a flexure that mimics a pivot, where this is a linear slide. Over here, there's a detent wheel and some toggles. We use this to make sure that my cat doesn't get overfed. These are detent slides. It's hard to see from here, but when you play around with it, you can see that one of the flexures is thinner than the other, and so that, of course, will affect the force of the detent. And then finally, this one, you can see that there's a little structure that's deformable in each of the holes, and that's a way to get like kind of a soft press fit on potentially like weird shaped things. This was another like kind of an assembly kit. This is what we did at the Hackaday workshop, the SuperCon workshop. And these fingers were inspired by the Festo multi-choice gripper. Festo has a bunch of really fun videos. I encourage everyone to check out their YouTube stuff. But basically, yeah, it's very like pleasing how the fingers deform around whatever they're gripping. So I have these here too that you're welcome to play with. This is probably my most recent Flexure project. This was kind of inspired very much by the Paul Henningsen Artichoke. This one does not cost $12,000, but is arguably also not as good in many ways. I use flexures a lot on this. So this features a kind of rib cage structure where the ribs themselves have lots of little flexure fingers, and these are what's grabbing onto each of the individual pedals. And then, of course, the whole rib cage is kind of kept together with, again, more of these flexure like snap-in features. So yeah, lots of cool projects. Here are just some more resources. This is a video which I think is the YouTube channel Veritasium basically took a tour of like this lab and made a video about it. So I think it's a pretty fun one to watch. Larry Howell and his Larry Howell is a member of this research group, and he and his colleagues have basically like written the books on compliant mechanisms. So if you like really want to dive in deep and get all the academic background, I think that's a great resource. Anyone who's interested in making their own grippers or demo boards, all the files for that are available on GitHub. So that's it. Any questions?
Interfacing fingers with features that allow them to interlock and retain themselves. But it seems like designing like a finger joint is like a 3-second super easy operation. Designing the right geometry to actually produce a flexure which can retain some other part seems considerably more complicated. Do you have any tips? Are there like scripts for some CAD packages or something that make it easier to produce things like these spring-loaded finger tab things?
You're referring to these and these, like both of them?
I guess both. Really, I think I'm thinking of the ones in the rib cage more than the one at the top.
Yeah. I think for me, a lot of these were guess and check. So I would design like one finger tab and like one tiny piece of a pedal. And I might make a piece where it has like 3 different finger tabs with like 3 different spacings, and I might just vary that. This is part of really like I'm telling you ways to get around having to do any simulation. And so, but once I have that geometry, like literally like the geometry that I used for this, I've used this on many, many projects now, and I literally have a CAD file which is just this piece and the holes that it mates with, and I will just like cut those bodies and merge them into whatever thing that I'm working on. So there is a little bit of guess and check, I think, to get the right fit, but once you have it, you can sort of cut and paste that into whatever project.
Cool.
Question, way back there. Do you have a CAD over there? That guy had, he's right there. You got his hand up.
is there a CAD package that you like to use that makes it easy to iterate and copy and paste and that sort of thing?
Yeah, I've been using Fusion 360 for all my stuff. I like it because it's not too expensive. For most work stuff, I've used NX, which I think in a lot of ways is much more powerful. But so far, I think Fusion has been great for everything that I needed to do. Yeah.
When you're prototyping these in Delrin with your laser, does the kind of the taper or kerf from the laser cause problems with kind of off-axis deformation?
For sure.
And do you have any strategies for dealing with that?
One good strategy is to not have your own laser cutter, so someone else is responsible for the machine maintenance. Yeah, definitely I found in some makerspaces, a lot of the lasers are not tuned such that the axis is actually perpendicular. And sometimes, if it's really off, then the angle of the kerf will change depending on where you put your part down on the bed, and that's super annoying to chase down. So first of all, every time I've sat down and wanted to do do a lot of cuts, especially over a large sheet, then it's always really nice to do a test cut at each corner and kind of make sure that the machine parameters across the entire machine are what you expect them to be. Otherwise, though, I find that, because of the kerf, there's really only the bottom part of the sheet that's ever really in contact with the other features that you've designed. And I find that, again, it's nice to do small little test pieces. So when I have two pieces where I know the fit is going to be really critical, I will just cut those two pieces, or even just the parts of those pieces that need to fit really tightly. And I found on my laser, for example, I know if I'm going to cut something, I should just do a standard offset of 0.15 millimeters for everything in order to get the right fit. So again, a little bit of guess and check would be my recommendation.
Cool, thanks.
So speaking of kerfs, if you want to try any of this on a 5-axis water jet, we should talk. But more to the point, question about the Delrin, because you were talking about plastics. There's a very interesting curve to Delrin. I've heard nothing but amazing things for how workable it is and all of that. Would you say Delrin is characteristics of plastics in general, or that perfect curve without the elastic region is characteristic of most plastics?
I think that plastics overall being not good springs is pretty characteristic of plastics in general. I think what makes Delrin good for a lot of projects is not that it's a perfect spring, but more that it's it laser cuts quite well, it's very machinable, it's not insanely expensive. And so I think all those factors make it really good for a lot of prototyping or maybe even small runs of parts. But yeah, I would say in general, plastics are not good springs. And if you need something that's going to permanently apply force, then plastic is not the material you want to choose. You'll have a really limited lifespan. Even in the example of the little spring flexure that's holding the this one here, Joshua said that a bunch of the tool holders are just holding tools for a long period of time, and so those flexures will actually lose force over time. In his case, it's just not that sensitive to it, so it's totally fine. But yeah.
So those characteristics, are they in the material data sheet, or do you have to dig in a little bit deeper in order to find out things like the elasticity of the various plastics are?
Yeah, I mean that curve I got just from Googling, and that's DuPont's material sheet for Delrin. It's interesting though, depending on what kinds of materials, I think for a lot of generic materials that you're using for just random side projects, you'll find readily available spec sheets, or you'll find spec sheets that are definitely good enough for what you're trying to do. Definitely for really performance stuff, it can, depending on how fast you pull the material or how you prepare the sample, those stress strain curves can vary a little bit, and so those data sets can get very proprietary. Especially if you imagine in order to do like a full-on simulation, you need to feed your simulation all of the data for like what are the material characteristics for this particular material. And so having really good characteristics to feed into simulations becomes sort of like an IP that people cling to. So depending on like how special is the material and how detailed of like analysis you need to go into it, maybe you'll run into some problems. But in general, a lot of this stuff you can just find online.
Sorry. I see in a lot of your Flexures that there's, or a lot of the pictures that are in this, that there are a lot of right angles, and I would imagine that those would be stress concentrators and that you get fractures at those points. So do you have any thoughts on how important it is to make nice smooth fillets and curves and things like that, or whether it's okay to just have, you know, right angles between your flexible elements and your non-flexible elements?
Yeah, I think that it definitely makes a difference, and in some of them, so yes, all of these do have some strain relief in them, and I think what I'm trying to fight is having a thin enough beam that the force is low enough to what I want it to be. But yes, there are stress concentrators. So this here is a good example. It gets, I think, less than 1 millimeter in all of these joints here, and that was really to make sure that like the force of having the fingers deform was like low enough. And so I did a couple iterations to see like how big I could get the radius to still have the force be that. I think if you can design a much larger flexure, then like definitely go for it. Depending on, you know, from like messing around, I think like these sizes of radii for most of these things is definitely sufficient. But for laser cutting, I think the other thing to worry about is that it is fairly high heat that's cutting in that region, so you actually do change the material properties, and I've noticed that specifically like if you make things really, really small, the material can get really brittle. So I think it's like stress concentrations, but there's also other factors that complicate it too.
Thanks.
One last round of applause.
Okay. So this is right now we're doing hardware happy hour and didactic, and this is the first time we've got rid of all the pizza before the talk started. So round of applause to all of you. Do we have any community announcements? Somebody said something. They would like to speak to the community about something. I know somebody did. Yeah.
Pass around.
See, this thing, as soon as one person does it, then all of a sudden there's more. Yeah. Hey, everybody, I'm Bo. You may know me from other meetups, such as the San Francisco Hardware Startup Meetup, which is one that I helped co-organize. We just did one earlier this week, but we also do it every month. We'll be back again in March, not on the same day as HDDG. But we're always looking for cool venues and speakers, and you can find us on Meetup. And speaking of meetups, I've recently started a new hardware startup for meetups, which is I'm trying to better organize all the events in the Bay Area, because there's all these awesome groups like this, but there's also ones in the South Bay and the East Bay and all of that. So I'm inviting 100 alpha testers to join me in this totally made-up adventure that's actually becoming a real thing.
Is it free?
It is totally free.
So
I announced this at our meetup earlier this week as a hardware startup meetup, and then I went to register on Meetup, and they like wanted money. Yeah. So I instantly went to Eventbrite, and then also we're going to roll our own. But anyways, in all seriousness, anybody that wants to can email me hi@bench.supply, no .com, just bench.supply. And you'll be part of this fantastic experiment, which will be me emailing you cool things of stuff happening around the Bay Area. And then aside from that, I'm also doing an event tomorrow night in Oakland, which if you were on bench.supply, you'd already know this. But actually, Morgan and I are going to be doing some hardware demos, and I'll also be buying you all food and drinks if you want to show up. It's at a great hardware co-working space called Circuit Launch. You can also find it on Meetup. And we're also doing DIY robocars there March 7th, which if you're not familiar with DIY robocars, check it out. Chris Anderson, who used to work upstairs editing Wired Magazine and started a lot of the DIY drones community, hosts DIY robocars. They do a quarterly race, also at Circuit Launch, with RC cars racing each other autonomously. And there's a free barbecue. So it is awesome, says Morgan. So come check that out as well. And then finally, since this is apparently a hardware meetup and demo and things, I don't know if all you, like me, are really into embedded electronics and always want to get closer to the metal. I have finally started programming in bare metal, and I don't know whose girlfriend is Siri. Let's torpedo that one. But anyways, speaking of hardware, this is my latest hardware project. It is literally metal, or an alloy known as aluminium to some. But I've recently started to learn how to do machining. So I made this on a manual lathe earlier today, and making actual hardware is really fun and cool. So I encourage you all to check that out. And if you're also into that sort of thing, I would love to actually know what the hell I'm doing, and totally open to tips and tricks and all those fantastic things. I still have all my fingers. Hopefully I'll be back next month with 10 as well. So that's basically how easy it is to come up here and just talk about random stuff. I'm sure it's inspired at least several more of you to come up here and try it out yourself. I see one volunteer. All right. There'll be more.
Yeah, come on up.
Come on up and introduce yourself.
Hi, so I'm Nick. I brought Evil Simon. It's just like the Simon from the 80s, but it has a very evil twist. I brought 4 of them. I'm also selling them at a discount from what I sell them on my Tindy store here tonight. But if you just want to play, that's fine too. It's really, really hard.
What else? There we go.
Hi, my name is Sandeep. I've got 2 quick announcements. So I've got a space in the dog patch that I run my business out of. I do custom manufacturing and test equipment. And I've got a bunch of extra space, and I open that up to other small businesses. And it's getting a little software-y in there. And so I'd love to get more hardware folks in there. I've got a Bridgeport with the CNC controls. I've got a 13-inch lathe with DRO, a 24 by 36, 90-watt laser cutter. And I'd love to have more hardware folks, because it's just great to have a community, especially if you're self-employed or a small startup. It's a great place to bounce ideas off each other. And the second announcement is I've overcommitted myself to a bunch of work. It's the consultant's life, feast or famine, and I'm in feast mode. So if there's any folks out here who are sharp engineering techs, you can turn a wrench, got a good attention to detail, can solder, anything along those lines. Looking for some kind of part-time work, please hit me up. I would love to get your assistance. Thank you. Yes. Oh, sorry. For the space, check out 695space.com or come find me. I'll give you a business card and you can shoot me an email. And for the work, come find me, or hell, go to 695space.com. You can get me there too. Cool. Thanks.
Who's next? Anybody next? You already had your turn.
No, I just going to grab my thing.
Is that it? Oh, we got one more. This thing's cool.
Yeah, so this isn't the first time I've come and shown this thing off, but a couple of the times before it's been a little different. I've gotten a lot of feedback from the folks around here on what to do. Originally, this thing was just a selfie stick with some electronics on it. Now I've got an NRF52 in here. I'd love to get your feedback on this device. It's actually, I should explain what it is. It's a device for picking up litter. Every time that we pick up litter, we take a photo of it, we get a GPS point, and we can tell where the city's improving, where it needs more attention, and just make maps of trash. But yeah, if you come check it out, give some feedback, it'd be great.
What? Are you up? You're up?
Hello, I'm Alex Glow. I have a weird thing. Where did the cable go? God damn. There we go. All right, so I'm really fascinated by biohacking, and in particular things that I call mind-hacking or mind-altering gadgets. And this newest one is one I've been working on for a while, but then I tried to turn it into a Wonder Woman tiara, and I got this instead. So what it is people are going to come at me and be like, you're destroying your eyes with blue light, but I'm not really. I'll tell you how. What it actually does is helps reset your circadian rhythms. So A, you can use it for jet lag, and B, you can use it for seasonal affective disorder if you have that. I don't, so I'm not going to say that you should. But yeah, there's a bunch of cool science around this, and there's already 5 companies doing similar products, only they look really stupid. So I think we can do better, and I'm going to be publishing a project on this soon. In the meantime, feel free to come and ask me about it. Thanks.
Oh yeah, this thing. I want to know what this thing is. Oh, what? No, it's this giant wood Ouija board.
Hello, everybody. Hey, I'm Noel, and this is Sick Luggage. It's a boombox. And it was inspired by the absolute lack of anything that resembled real boomboxes out there that I wanted to rock down the street and start a party with. So that inspired the invention. Been prototyping, gathering partners, gathering friends and family around the project, and it's kind of like just a slow growth passion thing. Hopefully one day it'll be a day job. So I'll play a song so you know what it sounds like, and then I'll tell you a little more about it. That's Krungbin. Anybody know how to spell Krungbin? Don't try. So the thing about Sick Luggage is we did a Kickstarter at Bo's insistence, suggestion, cajoling when... What's that? Clarissa started it, yeah, at Shapeshift. Well, Shapeshift was the theme of October Kickstarter, so we decided to build a recycled product. This is a wine crate it's built off of. And our main objective in doing the Kickstarter was just to get off the dime and actually get into market and take the pain of being a real product and having real customers for the first time and stop prototyping after the 26th prototype in 3 years. And it was a great experience. We didn't try to sell too many more than we could build. And it was a real lesson in just campaigning to the test. And our test in the end was, do people want to build their own boombox or do they want to buy one? And testing price sensitivity and so on. And of course we got screwed because the results was exactly ambiguous, half and half. And so there's other characteristics to the boombox, including that you can build it yourself. It also has this removable faceplate that allows you to, now that you can see the sort of core box, this is the cedar heart and soul of it. So the ability to connect to your audio device, you can also flip it over, and then now you can see you can put your album cover on it. It can be branded, customized. We have under development a print-on-demand. This is called Vibe Face, that system. And we're really stoked about it, mainly because people, I think, are too much in their own zone in their headphones and being alone. And we're trying to get back to that time of, earlier on when music was about gathering together and making friends and connecting around that experience. So really that's what this is all about. It's a hardware running around as an excuse for a social experiment to see if we can just start more parties and be more human together. So if you're interested in that, talk to me. We're figuring out what to do next, trying to scale to the next 100, next 1,000, et cetera. And then build a local manufacturing model where people can participate by just being a builder or being a customizer in different cities. So that's the vision there. I quit my day job in software. I'm very excited about that. Yeah, Monday is my last day officially. And so I just said, to hell with it. I bought a nice new video camera and reminded myself how much I love video production. I'll be live streaming the event and upcoming events with Bo and with Morgan at Circuit Launch. If you have a startup and you want product videos, demo videos, explainer videos, music videos, whatever, live streaming services, let me help you at the friends and family rate while I'm building my reel and building my chops back up. So that would be fun too. If you need video, talk to me. Thank you. Sorry I went on a little bit. Oh yeah, Noel at sickluggage.com. And It's sick. It's luggage. Please remember that if you can.
Cool. Anybody else? Nobody? Oh, wait. One more? Okay.
I have a question. So my project is less portable than some of the others. It's that 9-sided object over there. Those are pixel purse panels. So it's a 16 by 288 pixels, running on a single Teensy 3.5. So the question I have, so 9-sided geometry is a little bit hard to program for, so I'd have like a 34 kilobyte lookup table. So nonagon versus nonagon. Can I get a show of hands for nonagon? Can I get a show of hands for nonagon? All right, nonagon wins. If you have any questions about it, let me know. My name is Garrett Mace, and I put the code such that it is as it is up on GitHub, and I will grudgingly give you the URL so you can look at my terrible C++.
Okay. Do we have any announcements for the hardware happy hour? No? You don't care? Hey, show up. Speaking of, we bought way too many shock tops, so if you're going to have another beer, have a shock top. What happened there? They just substituted? Okay. Okay, so right now, I guess we're going to hang out here for like another half an hour, and then we are going to the after party somewhere down there. It's Alchemist? Is it Alchemist? And it's Alchemist, right down the street. And then I need to get out of here to go to a CBD mud bath. I'm not kidding.